Hi, my name's Evan Olson, and I'll be solving problem 2.42 of the Fundamentals of Heat and Mass Transfer 8th edition. The problem statement says that there's a thin electrical heater dissipating 4,000 watts per meter squared, which is sandwiched between two 25 millimeter thick plates whose exposed surfaces experience convection with a fluid for which the T infinity temperature is 20 Celsius and the convection coefficient is 400 watts per meter squared Kelvin. And it gives us the thermophysical properties of the material. Part A says that on Tx coordinates, sketch the steady-state temperature distribution for between minus L and plus L, with 0 centered at the electric heater. So with part A, we can assume that this is a steady-state system, since we want to find the steady-state temperature profile, that the material properties are isotropic. It's symmetrical about x equals 0 since the surface conditions are exactly the same, and that there's no heat generation inside of the wall itself. We can start off with the heat diffusion equation, which you can get rid of the yz. You can get rid of the yz in time terms, and also since there's no heat generation, that also goes to 0. And since we have constant material properties, we can pull that k out to the outside. And since the right side is 0 anyway, we'll just cancel out. After, we're just left with d squared t over dx squared equals 0. And we can just integrate that twice to find what the temperature distribution will look like. And that equation would turn out to give us t of x is equal to c1x plus c2. And that's our general solution. To find those constants, we can use our boundary conditions. First, we have at x equals 0, we know that there is a constant heat flux, so we can set the minus k dt dx at x equals 0 equal to q, or that q0 heat flux. And at each boundary, we have that same condition at x equals L and x equals minus L, and that's equivalent to the convection coefficient to the air times the temperature delta between the surface and the fluid temperature. Starting off with our first boundary condition at x equals 0, we just have that the conduction is equal to our heat flux. If we plug in our dt dx equation, which is equal to c1, into this, we get that k minus kc1 equals q0, and then we can solve for c1 to just get that c1 is equal to minus q0 over k. We can then use the second condition at plus L, and this will be equivalent at minus L. And we can use the same value for dt dx, and we get minus kc1 equals h times c1L plus c2, since we're using this t of x equation at x equals L. We can then rearrange, plug in our value for c1, and then we get this equation. We can then find c2 out of this, and then we find that c2 is equal to q0 over h plus q0 times L over k plus t infinity. If we plug these back into our original equation for t of x, we get that this is our specific solution for these boundary conditions. For x less than 0, this will be the same equation, except the slope of the constant before your x term will be the opposite. When you bring all of these together into a piecewise equation, this is what the specific solution for this case is. And plotting that in MATLAB, this first curve is what that looks like. You can see that the temperature is higher on the inside towards the heater, and it drops down linearly as you reach the edge of the block. Part B says consider conditions for which there is a loss of coolant and existence of a nearly adiabatic condition on the x equals plus L surface. On the Tx coordinates used for part A, sketch the corresponding steady-state temperature distribution and indicate the temperatures at x equals 0 plus minus L. Label the distribution as case 2 and explain its key features. So, part B says that now we only have a convection condition on the minus L side, and on the x equals L side, we have an adiabatic condition. And what that means is you essentially just set your k dt dx term equal to 0. And this means that the temperature curve is going to have 0 slope at that side, meaning you're going to have a completely flat curve. And that's implying that the temperature at L is going to be equal to the temperature at 0. And so we can find out that the temperature curve is going to be the same on the 0 to x equals minus L side, and then the temperature curve on the right side of the block is just going to be constant as soon as you reach 0. So we get the same value for C1 as in part A, and we get the same value for C2 as part A as well for x less than 0. And then for t of 0, we can just to find the temperature at 0, we set this equation equal to we set this equation here equal to 0, and then this is the C2 coefficient falls out, and then this becomes our piecewise equation describing this condition, or this case. When we plug this in to MATLAB using the values of the problem, this is the curve we get, the second curve. You can see that since it's adiabatic on this side, the temperature curve remains constant, and since the heat is able to leave on this side, it drops down linearly. Part C says, with the system operating as described in B, the surface at x equals minus L also experiences a sudden loss of coolant. This dangerous situation goes undetected for 15 minutes, at which time the power to the heater is deactivated. Assuming that there's no heat losses from the surfaces of the plates, what is the eventual as T approaches infinity uniform steady state temperature distribution in the plates? And just plot this on the same Tx axis as the previous. So this question's a little bit unique from B. Instead of just introducing a new boundary condition, we also have an initial condition of the problem. We know that the temperature curve is going to be completely uniform, meaning it's going to be completely flat on the Tx axes. So if I draw some Tx axes here, we know it's going to be completely flat at T equals infinity because the temperature has had time to completely steady out. So the way I solved this problem was I wanted to find the total thermal energy of the system assuming that there was no heat loss in the system after part B, and just to find the steady state uniform temperature of that. To do that, you can find the mean temperature of the system, and you just do that by by this equation. So we know the equation for part B, and we can just take 1 over 2L, the integral between minus L and L of that temperature distribution, which is this equation right here. And plugging all the values for that in, we have to split it between minus L and 0 to L because it's a piecewise. And then we go through the steps of integration here, and we can cancel out some terms, and then we eventually get to the average or the mean temperature equation being this here. And then if we plug in the values for the problem, then we get a mean temperature of the part B of 45 degrees Celsius. Now, with that information, we have to find how much energy was put into the system over the period of 15 minutes, and this is just going to you're going to sum up the amount of thermal energy which was added, and then determine the delta T. So we can just do this by setting the Q. We can do this by setting Q equals the heat flux times the area times the time. And that will give us a unit in watts. We can then equate that to MCP delta T, since that's the energy stored within the system. And then we can combine all of this together and solve for delta T. So we start off by putting QAT on the left side, and then we divide by MCP. We know that the mass in the system is equivalent to the density times the volume, and the volume is equal to 2 times the length times the area. So that's the entire volume of the block. And then we can cancel both the area term, since we don't know that dimension in the system, and then we just get an equation of Q times T over 2 rho Cp times L. If we plug in the values of the system, we get a delta T of 41.1 degrees Celsius, and we can add that 41.1 degrees Celsius to the 45 degrees Celsius mean temperature that we found here to get our steady state temperature at 15 minutes of 86.14 degrees Celsius. And if we plot that curve on this subplot here, we can see that it's just constant along the entire block since it's completely uniform. And it's also much higher than the previous systems since there was no ability for any heat to escape. Part D says that on TT coordinates, sketch the temperature history at plate locations x equals 0 and plus minus L during the transient period between the distributions for cases 2 and 3. Where and when will the temperature in the system achieve a maximum value? So what this is asking us to do is between B and C, where we added that adiabatic condition on both sides, the block is no longer able to dissipate its heat, and so each location along the block is going to see an increase in temperature. And we want to plot that increase in temperature with respect to time. Now, this isn't so easy to do analytically, since it is a transient. And so you can estimate the temperature distribution over time. You know that the temperature distribution has to follow a exponentially decaying curve reaching a limit, since that's the behavior of thermal systems generally. And we know that at x equals 0, that's where the heat is being pumped into the system, and so that's going to reach that steady state temperature the fastest. Next, we have x equals plus L, which was already at a higher temperature than minus L, so that's going to reach it second. And we have at x equals minus L that started at 30 degrees Celsius. So to get to that steady state temperature of 86 degrees, it will take the longest amount of time. And the maximum temp is going to be reached at x equals 0, and it's going to be reached at x equals 0 the earliest, since that's where the heat is being put into the system.